Hello everyone, Foxy here, and welcome to Mostly Mental. Once again, Aurora has found an exciting new game for us to play. This one's called Domineering. We have a grid of squares between us, and we'll take turns placing dominoes onto it. I can place my dominoes vertically, so they cover up two squares like so, and Aurora can place hers horizontally. As usual, the winner is the last player who can make a move. So a sample game might look something like this. And now Aurora gets one last move, and I can't fit my domino anywhere in here, so she wins. Good game. It's certainly a fun game, but I clearly haven't got the strategy down yet. What can I do to make sure I win the next time around? As always, we'll start by analyzing some small cases. And a natural place to begin is with the 1x(n) rectangles. Clearly, if there's only one square, or no squares at all, then neither player can make a move. There just isn't enough space for a domino. So these are losing positions for whoever goes next. Okay, then what about the 1x2? Well, there's still no space for a horizontal domino, so Aurora still doesn't have a play, but now I can place a vertical domino. So if Aurora goes first, she loses immediately since she can't play, and if I go first, I can play, and then Aurora can't. Either way, this is a winning position for me. And in fact, that'll be true for all of these rectangles. I win regardless of who plays first. But in some sense, this feels like it should be more of a win than this. Here, I can only play one domino before I run out of space, but here, I can play 3. So from this position, I should have more of an advantage than from this one. How can we make this notion more concrete? Let's introduce some notation. We'll describe a position by 2 sets. One for the positions that I can move to, and one for the positions Aurora can move to. We'll write these sets in brackets, separated by a vertical bar, like so. For example, from this position, I can put a domino here, which gives us this position, or I can put a domino here to get this position, or Aurora can put a domino here to get this position. So we'll describe our starting position with these 2 positions on the left for my moves, and this position on the right for Aurora's move. And then we can repeat this process with each of these smaller positions. From here, I can't do anything, but Aurora can make a move like so, which gives us this position. And from here, neither of us can make a play. And here, I can place a domino to get to this position. And we'll keep going until we get to positions like each of these, where neither player has any available moves. And now we can start assigning values. These positions down here with no moves aren't really useful to either player, so we'll say they have value 0. And this position where I can make a move but Aurora can't gives me 1 move's advantage, so we say it has value 1. And similarly, the position where Aurora can move but I can't gives me 1 move's disadvantage, so it's worth -1. Okay, then what about our starting position? Well, it's got positions worth -1 and 0 on the left, and a position worth 1 on the right. So its value ought to be somewhere between these and this. And the most natural choice is 1/2. So this position is worth a half move for me. And all of this may sound familiar if you've been watching this channel for a while. If we require all of these values on the left of the bar to be less than all the ones on the right, then we end up with a structure known as the surreal numbers. I've already made a whole video on the subject, so if you want to know more, I'll link that in the description. In this video, I'll just call them numbers. But not every position in domineering gives us a number. For instance, consider this smaller L shape. I have only one legal move, where I place this domino vertically, which leaves a single square. And there are no possible moves from there for either player, so this resulting position has value 0, and our starting position needs to have a 0 on the left. And similarly, Aurora's only move also only leaves a square, so there should also be a 0 on the right. So we end up with 0, 0. That no longer has everything on the left smaller than everything on the right, so it isn't a surreal number. There's just not a value we can fit between 0 and 0. The position's value is actually a nimber, star, but that's not too relevant for our purposes today. We can take this idea even further if we look at a 2x2 square. If I play vertically first, then we're left with space for another vertical domino, but no space for a horizontal domino, so there's 1 point of advantage here, which means there's a 1 on the left for this position. And similarly, if Aurora plays horizontally first, then I can't play vertically, but she can play another horizontally, so she has 1 point's advantage, which means there's a -1 on the right. So this 2x2 square has value 1, -1. Now the left side is actually larger than the right. And positions like this, where the bounds are two numbers out of order, are called switches. But what's going on here? What do these strange values even mean? Before we answer that, there's one more useful observation we can make. Say we've got a position like this one. We've both made some moves, so there are already a few dominoes on the board. Notice that the remaining empty spaces are split into two distinct regions. And these regions are independent. No domino I place over on this side can in any way change the shape of this region over here. So in effect, we've got two separate games going on at once. And each turn we choose one of the two to play in. We call this the sum of the two games. If the values of these games are numbers, then these sums work as you'd expect. Adding a game with value 2 to a game with value 3 gives you a game with value 5. If instead we have a number and a switch, then we just add the number to each side of the switch. So 3 plus 1, -1 is 3 plus 1, which is 4, and then 3 plus -1, which is 2. And we can use this to write any switch as some number plus a switch centered at 0. So for example, 8, 4 is 6 plus 2, -2. We can think of this mean value as the closest number to this non-number value. What about the sum of two switches? For instance, what's 5 negative 5 plus 1 negative 1? It's not quite so obvious. To figure it out, let's explore all of the ways that this sum of games could play out. On the first turn, if I get the first move, I could choose to play in this first game, leaving the second alone, to get 5 plus 1 negative 1. That is 6, 4. Or I could choose to play in the second game to get 1 plus 5 negative 5, which is 6, negative 4. And similarly, if Aurora goes first, then we'll get to 4, negative 6, or negative 4, negative 6. And then expanding further, from this position, I can move to 6, or Aurora can move to 4, and so on for all of these other games. But now notice that every outcome from this branch is at least as large as the corresponding outcome from this branch. If I get the next move, then I'll end up with the same value, and if Aurora gets the next move, I'll end up with a larger value here than over here. So I'll always do at least as well choosing this first move. This other move is just a bad idea. We call that a dominated move. So if we're both playing correctly, we really don't need to consider this move further. We can just discard the whole branch. And similarly, Aurora would never choose to play here, so we can throw out this branch too. So what we're left with is just these two positions here. So the sum we're looking for will be equal to 6, 4, negative 4, negative 6. And there's another way we could think of this. We could imagine this game as having a pile of money in front of us. On each turn, a player can choose to take one bill. Of course, the best option is to go for the largest bill first. So the first move should take the 5, and the second move should take the 1. These 4 values here correspond to the 4 possible turn orders. If I get both moves, then I get the 5 and the 1, which gives me 6. If I get the first move and Aurora gets the second, I get the 5, but Aurora gets the 1, so I end up with 5 minus 1, which is 4. And these two correspond to the other 2 orders, where Aurora gets the first move. Hang on, why do we need all 4 of these turn orders? We said at the start that Aurora and I will alternate turns. So we shouldn't need these 2 options where someone moves twice in a row, right? Well, let's take one more look at our game. As we've said, it's equivalent to having 2 bills on the table in front of us. If we alternate turns, then I'll end up with the 5, and Aurora will get the 1, or vice versa. Either way, the 2 bills will go to different players. But what if we add in another switch with an intermediate value? Let's say 2, negative 2. Well, that's like tossing another bill into our pile. Then the play will go 5, 2, and 1. So now the 5 and the 1 go to the same player. And that's really what these values are telling us. Even if the game as a whole alternates turns, the turns we spend in this component can give us these values when we consider this as a term in a larger sum. So now we know how to find values for sums of games, at least for numbers and switches. But if we have two games on the table in front of us, how should we decide which of them to play in first? Say we have a position like this one whose value is a number. That means that every position on the left, that is, the positions I can move to, must have a lower value than the current position. And every position on the right must have a higher value. In other words, every move that I can make reduces my advantage. And every move Aurora can make reduces hers. So I'd rather she play first, and she'd rather I play first. Neither of us really wants to make a move from this position. On the other hand, we saw this position is a switch with value 1, -1. Which means that if I play, I gain a point, and if Aurora plays, I lose a point. So I really want to play here before she does. We call a game like this that we both want to play in hot. And a game like this that we want to avoid is cold. For switches, the bigger the spread between the bounds, the hotter the game becomes, and the more we both want to play in it. So a game with value 5, -5 would be hotter than either of these. And that makes sense. That's the $5 game we saw earlier, and we said that that was a better choice than the $1 game. The width of a switch, or rather the half width, the distance from the bounds to the mean value, is known as the temperature. So the temperature of this switch is 5, and the temperature of this one is 1. In general, the winning strategy is to play in the game with the highest temperature. This notion of temperature is useful for switches and sums of switches, but what about for other games which aren't switches? Can we generalize our definition to work for any game? Well, in some sense, the temperature of a switch tells us how much it would cost us to play somewhere else. For instance, if we have the position 5, -5 plus 1, -1, choosing not to play in this first component means I have to accept a penalty of 5 from Aurora playing there instead. And similarly, choosing not to play in the second component means taking a penalty of 1. And that matches up with the temperatures we saw earlier of 5 and 1. We can use this idea as the basis for a more general definition of temperature. We'll introduce a tax, t, for any move in a game from a position whose value isn't an integer. So under this tax, 4 is an integer, so it's still worth 4, but 4, 2 isn't an integer, so now my move is only worth 4 minus the tax t, and Aurora's move is only worth 2 plus t. And this tax applies to every move, not just the first, so 3, 2, 1 becomes 3 minus t, 2 minus t, 1 plus t, plus t. So we're applying the tax to the first move and to the second. For very large t, the tax is more than the value of any move, and neither player will want to play. So if t is 1,000,000, then this left side becomes very negative, and this right side becomes very positive, so I would much rather wait for Aurora to make a move, and she would rather wait for me. But as t gets smaller, any non-integer position gets more and more attractive. So if t is 0, then this becomes 4, 2, and we'd both rather make the next move. The transition value, where players go from avoiding the game to wanting to play, is called the temperature of the game. So here, when t equals 1, the two sides meet up. And so the temperature of this game is 1. This general definition lends itself nicely to a graphical interpretation called a thermograph. We can plot the values on the left and right sides of a game as functions of t. So under our tax, the switch 4, 2 becomes 4 minus t, 2 plus t, and if we plot these two functions, we get a plot like this. By convention, we take this graph and rotate it to get this, so that the temperature increases as we go upward. Note that this does mean that the value increases from right to left instead of left to right, which does feel backward. But at low temperatures, which is what we really care about, my moves will be on the left and Aurora's will be on the right, which matches how we write them in our notation. Yes, this convention is a bit confusing at first, but I promise it's natural once you get used to it. In this graph, we can clearly see that the two lines meet at a point 3, 1. This tells us that the mean value is 3 and the temperature is 1. At any higher value of t, Aurora's moves are worth more than mine, so the red line is to the left of the blue line, which means that neither player wants to play at such a high cost. And we can represent that by cutting off the lines at that point and drawing in a vertical stem at the mean value. This final plot here is our thermograph. Let's try a slightly more interesting example. What's the thermograph for 7, 4, 2? We can start by drawing the thermographs for the left and right sides separately. The left side, 7, is just an integer, so it's tax exempt, and we get a vertical line at 7. And we just saw a moment ago, the thermograph for 4, 2 looks something like this. Now, each of these positions is a move away, so we'll need to apply the tax to get there. We subtract t from the left, which shears this graph to the right, and we add t to the right, which shears this graph to the left. And we end up with something that looks like this. Once again, the graphs intersect at a point here, 5, 2, so the mean value is 5 and the temperature is 2. It looks like we've got 3 branches down here at the bottom, but our thermograph should only ever have 2. One for my next move and one for Aurora's. As we saw earlier, these branches correspond to different move orders. I move next, Aurora moves next, then I do, and Aurora plays twice. And this time, there's no way to stick in extra moves from somewhere else. This is the whole game. So we only care about the 2 branches corresponding to alternating turns, this one and this one. So we can throw out this branch, and our combined thermograph will look something like this. Let's try out one last example. Let's find the thermograph for 1/2. We've previously seen that 1/2 is -1, 0, 1. Now, that -1 is a dominated move, since 0 is always better, so we could just throw it out and be left with 1/2 is 0, 1. But for the sake of discussion, what does a thermograph look like for a game with multiple options for one player? And what does it let us say about dominated moves? When we apply our tax to this game, we get -1 minus t, 0 minus t, and 1 plus t. plotting each of those functions, we get these three lines. At any given temperature, my best move is the one with the most value. That's the blue line that's furthest to the left. In this case, that's always going to be this line at 0 minus t, since the other choice is dominated. In fact, that's a way to recognize a dominated move. Its thermograph is never the one furthest to the left. Or for Aurora's moves, it's never furthest to the right. Okay, so the best moves for each of us give us these two lines. And they meet at a point, 1/2, -1/2, so this will be our thermograph. And the mean value is 1/2, which is why I said earlier that 1/2 was the most natural choice of value, and the temperature is negative. Actually, every game with a number for a value will have a negative temperature. And every game with a negative temperature has a number for a value. There's a lot more to say about domineering, temperature, and thermographs, but this video is running pretty long, and I've thrown a lot of tricky ideas at you already. And as with all difficult concepts, the best way to get a handle on those ideas is to play around with them for yourself. So here are some exercises for you to try. Post your answers down in the comments. Normally, this is the part of the video where Aurora and I would have a rematch. But domineering is still an open problem. No one has found a general winning strategy. And even relatively small positions have only been solved with exhaustive computer search. So starting from an empty board won't give us a lot of insight. Instead, let's look at a position partway through a game where we can use the tools that we've developed. Here we have a board with some dominoes already played on it. What should my next move be? Well, there are 4 independent regions left uncovered, so we can treat our game as the sum of 4 smaller games. This game here doesn't have any space for a domino, so it's worth 0, and we can safely ignore it. These 2 games are variants of ones we've seen before, and they're worth -1/2 and 0, respectively. And this last game we can evaluate by considering possible moves. You can check for yourself that my best move is here in the middle, these other 2 moves are dominated, and that's worth 2 points for me. And either of Aurora's moves leaves us with an L worth 0, and a worthless square. So in total, this position is worth 2, 0. Okay, so where should I play? As we've seen, I should prioritize the game with the highest temperature. To find that, we can draw the thermographs for each of our smaller games. And we see that they have temperatures 1, -1/2, and 0, respectively. And 1 is the largest of these, so my best play should be in this game, and as we've said, at this position. Once I've played there, that cools this game off, which means that this is now the hottest game on the board. So Aurora's response will be to play here. And we'll proceed in this way until one of us runs out of moves. That's how you can use game theory to win at domineering. Thanks again to Aurora for teaching me such an interesting game. Of course, there's always more exciting game theory to learn. If you find it anywhere near as fascinating as I do, and you want to see more, please let me know. I'd love to hear from you. Thank you for watching. I hope to see you again soon.